Hello everyone. In this session we will continue to build the substructure of our bridge. So please load your model from the previous session. So you will have the geometry like you see here in my screen. So to continue to build our substructure, as you see here we have our abutments and piles. So we will continue to build our center bend, the cap beam, columns, and foundation. So to work easier here and see everything, we are going to use ADA's mask feature. So if you remember from our grillage model, we had some supports here in the middle of the bridge. So we are going to change these supports and apply the coming force from the girders to a cap beam here, and after that the forces will be transferred from cap beam to the columns. So here I'm going to show you how to define the cap beam and the columns. So first thing we need to do is masking these nodes. So just select the nodes, go to the support mode, hold Control and click the supports and mask them using this icon here, or simply just by pushing M. So as you see here, I have masked the supports, and right now I can work much more easier on these nodes. So the first thing that we need to do is connecting these nodes to my cap beam. So to define extra nodes on my cap beam, I will copy and paste these nodes in the places of the cap beam. So select the nodes, Control C or copy, and here I'm going to copy them in Y direction, minus 0.6 meters. Click OK and Control V. So you will have the new nodes here. These nodes are located on our cap beam. And because all of these nodes are going to be normal nodes, they are not supports, we need to change all of those to normal nodes. So select all of them, use a Control H, or you can go to node mode, select them, use Control H, and here as you see their type is support, so we will change them to normal. So just click here on the column, select all of the column, right click, replace, and change those to normal nodes. So right now they are all normal nodes. So the next stage is to connect the nodes on the cap beam to bottom of our girders node, these yellow nodes here. So we will use ADA's rigid links to connect these. So you can go to member mode, click add, and start adding our rigid links. So here in the behavior, we will define these members as rigid links or rigid members. Click OK. and same for the others. Rigid, okay. And okay. So right now I have connected my girders to the nodes on my cap beam. Next stage is to define the nodes for the columns. So in this project, I will have 3 columns that they will be placed in the left, right, and middle of the cap beam. So we will start by defining the coordinates of those nodes that the nodes we will help us to define our columns. So we need to add some new nodes here. The coordinates of our new nodes will be like this. So just go to the node mode and click Ctrl H. And start by adding our new nodes. So I'm going to start the naming from 3000 maybe. So they will be normal nodes, and the coordinate x of the first one will be 4.5 meters. The y is minus 2.42, same as the elevation of our cap beam, and our z will be the middle of our bridge span, so it will be 48. Next one, it will be 9.5, and I will use same coordinates here, so copy and paste easily. Copy and paste. And the third one, 3002, will be minus 0.5 meters, and same coordinates for y and z, or y or z. Control C, Control V, Control C, and Control V. So if you click OK, you will see that our new nodes have been defined here, and we will use these nodes to add our columns. So the next stage is to add the nodes for the bottom of columns. The lengths of our columns are 4.9 meter. So the easiest way is just copying and pasting these 3 nodes in y directions at the bottom. So just select those nodes, Control C to copy, and I will use y direction minus 4.9 meters. Click OK, and use Control V or paste to have the nodes generated here down. So these are the end nodes of my columns. And now we can add the column members. So we can go to member mode, add, and click for the first mode and the end node or second node. So our columns, their behavior will be standard. The properties, they are concrete columns, the circular section with 1200 millimeters of diameter. So go to this icon here to define the section. Concrete, rectangular or round, round CON, and here you can find your 1200 diameter members here. And if you check for the characteristics, as you see, it's a circular section with diameter of 1200 millimeters. Okay, click OK. And the material, let's use the same concrete 030. And for the dead load, yeah, let's use our self load as dead load here. The self weight will be added to our dead load. And activate design criteria. We want ADA to design the columns. And the other one are standard. So click OK. So as you see, the column is placed here. So let's add the second one. Just click the first node and the next node. Same here, OK. And the third one. Okay, so right now, as you see, we have defined the columns. Next stage is to add our cap beam here. So our cap beam has also some extensions here and here after the columns. So firstly, let's add those extension nodes here, and after that we will define our cap beam. Or for simplicity, let's go with just these nodes here. But if you want to have some extensions to be designed on your cap beam here, you can add extra nodes and connect the members. So to add our cap beam, go to the member mode, click add, and start to click the nodes like this. So the section for our cap beam will be a rectangular. Rectangular 1200 by 1200. So just click the icon here and go to rectangular concrete CON, and here we can select the 1200 by 1200 rectangle or square. Click OK and OK. So as you see, the section is assigned to our column. Material, let's use the same things, dead load, activate design criteria and click OK. So as you see, our cap beam is defined here. And let's continue with the others. So just click this node here. Okay. And the final part or section here. Okay, so we have defined our cap beam, and these nodes are already connected to our girders. So because right now the end conditions of our rigid links are fixed, and all of the moments or other forces coming from girders, they will be transferred to cap beam. But here we want to have hinged restraints here. So we need to release end of these rigid links for M direction. So in that case, we will have hinged connection between the girders and the cap beam, and we will free the rotation here. So to release that, simply go to extended window mode, member mode, select the small rigid links, and hit Control H. After selecting these small members, just press Control H. So here, as you see, they're all fixed figs. I'm going to change the end constraint, one end or top constraint of those members to be hinged. So just click the column here, right click, replace, and change this one so the end will be hinged. For MX, same for MY, and MZ. Okay, so if you click OK, you will see that the rigid links there, they are released for the moment, and the bridge deck or girders will be free to rotate on these rigid links. In the next stage, because it is a concrete design, and if you remember from our concrete design session, we should add some rigid extensions in both ends of our concrete members. So let's start with our columns here. So go to the member mode, select the first column, hold Control, second one, and the final one. Press Control H, and here in the spreadsheet, go to our connection tab here. And for alignment for our rigid extension in Z direction, which is our longitudinal local axis, just click this column here, replace with face of support. So ADA will automatically assign the rigid extensions for EZI, and same thing for EZJ. Replace face of support. Okay. So if you see, automatically ADA assigned the end condition or end rigid zone, and it's -600, which is the rigid zone of cap beam and the columns. So click OK, and if you double click the column again, go to connection mode, connection tab, you will see that it's automatically assigned. So click OK. Also, we will use the same method for our cap beam. So select our cap beam members, Control H, and in connection tab for EZI, replace to face of support, and also for J end, same thing, replace face of support, and click OK. So if you double click again in one of the members, and check for connection, you will see that it's already assigned our rigid extension. So click OK. And also in this project, I want to define my design for shear for all of the members. So select all of the members and hit Control H. If you go to Concrete Design tab here, you can always change the considered shear to be in a D or DV or support face. In this project I'm going to use support face, so replace at face of support, okay. So click OK. So if you now press D to unmask everything, you will see that the columns are placed. And you can always check for the coordinates of the nodes at the bottom of column. So don't forget to save your project, so click save here. So next stage is to assign our design specification for our concrete members here. As you remember, we have already assigned the design for our girders and other elements in our bridge. So to assign the design specification for our concrete members here, we first should check if they are already defined as continuous systems. So go to this icon here, continuous systems, and select those. So as you see here, they're already and automatically built as continuous systems. So mask those like this. And because right now they are selected, just press Ctrl H to bring up the spreadsheet of design and start by assigning the design properties. For the continuous systems. So as you see here, I have S1 for the cap beam, S2, S3, and S4 are the columns. You can even view those continuous system numbering using view options menu. So go to view options menu or press O, and here down here we have a check mark for continuous system number. So if you put the check mark here, click OK. As you see, ADA will show you the number of continuous systems. So as you see here, S1 is the continuous system for my cap beam, and S2, S3, and S4 are the numbering or naming for the columns. So select them again as continuous system, Ctrl H, and start by assigning the specifications. So here I'm going to assign S6. So just select this column here, right click, replace, and let's select S6 design. Click OK. The interaction for the cap beam will be bending and columns will be bending compression. That's okay. And here we will assign the cover for our continuous systems. For simplicity, I'm just going to assign 70 millimeters for all of those. So just click the column here, select all of the column, right click, replace, and put 70 millimeters for top. Same for bottom, right click, replace 70, and we are going to use the same number for left collar, replace 70 millimeters, and right cover. Okay, so you have other properties here that right now I'm going to use the default numbers. So click OK, and right now we have defined our design specification for our bend. The next stage is to assign my foundations to the bottom of our columns here. If you remember from the previous session, we have already defined our deep foundation for pier. So if you go to structure, foundation models, and deep, we already defined our abutment foundation and our pier foundation. So it's already here. If you have not done it in the previous session, so please do it right now, and you will have foundation definition for pier. So to assign that foundation to the bottom of the columns, just select these three nodes at the bottom of columns. One, Alt Control, Control H, and change those to supports. Click OK. And right now, if you click on the support mode, go to the support mode, double click on the support. In the support tab, you can here assign the foundation to this support. So just click this drop down and assign the pier foundation to this node. Click OK. So as you see, my deep foundation with piles is already generated and assigned to this foundation, and we can use the same for the other two and this one. So drop down, pier, okay. So our foundations have been assigned to the bottom of columns. And if you unmask the structure, here is the full structure with columns, pile cap, and the foundations. And as you see here, ADA automatically defines the springs, lateral springs, or soil interaction with structure. They're automatically calculated based on your soil strata. In the next stage, I'm going to show you how to define some temperature variation, temperature gradient, and defining a soil pressure, active soil pressure for the abutment walls. So as you remember from our first model, the diaphragm, the grillage model, we already defined some of our load cases here, definition. So they are mostly dead load cases. So if you want to add temperature variation mode for the columns, I'm going to show you how to do that. Just add a new load case here. Let's name it as K plus, as positive temperature variation. And here in the drop down list, go to S6, and here if you drag down, you will see we have temperature here. So select this for our positive temperature variation, and here in temperature, just remove this X, because in high temperatures we don't want to add any snow or ice to our combination. Also, you can add negative or minus temperature variation. So define a new one, other new one here, and name it as K minus. Again, it will be S6 temperature, and for this one, let's activate the snow and ice possibility in case you have already defined a snow or ice load case. In this project, we didn't define anything. And let's add another one for gradient. So I'm gonna name it as T gradient. And in the drop-down list here, go to S6, and this time we are going to select this one, temperature gradient. And also let's add another load case for our soil pressure for the abutment walls. So I'm gonna name the other one as soil press. And here in drop down, S6, if you check here, I have pressure from soil. So we assign this type to the soil pressure. So we have added 4 new load cases, and we need to assign those to our members. So click OK. And in load case mode, just click it here, go to your K plus or positive temperature variation, save project, yes. If you remember, we already defined some selections for our main girders. I'm going to just apply this variation to the main girders here. So using Control K, select your main beams or main girders. Okay, mask them. So as you see here, just we have selected our main beams. To assign K plus to main beams, just select all of the beams. After selecting all of the members, use Control H, or you can use this icon here, Properties, Control T, to open the dialog box for assigning the loads. And here, because it's temperature variation, we go to this tab here, add a new column. And for K plus, let's assign 28 degrees of temperature variation, positive. Okay. So it's already applied to our girders. Also for K minus or K negative, select it from here. The members are already selected, so just click this icon here or press Ctrl T, temperature variations. And for this load case, let's assign a minus 40 degrees. For top and bottom fibers, click OK. So it's assigned. And let's assign our temperature gradient also. So it was T grad load case name. Go to Properties, Temperature Variations, and here I'm going to add a 30 degrees of variation between top and bottom fiber. And here in the last column, define it as thermal gradient and click OK. So here I have assigned my loads for temperature gradient. And the final load case that I want to show you here is defining soil pressure. So press D to unmask other members, and we are going to add our soil pressure to the abutment walls here. So to make it easier, just go to plates mode here, select the plate elements and mask them. So we will work just on our plate elements here. And to assign soil pressure, if it's a triangular one, you can always start from the bottom plates and change the load or the force, decrease it from the bottom to top, or you can always select all of these plates and assign just equal or same load pressure. So it's the way to do it manually, but we will see that in ADA you can also do it automatically using our tools, generators and abutment generator, that here ADA will automatically assign the soil pressure. Here I just want to show you how to do or modify it manually. So to assign it, you can go to soil pressure load case mode and select the place that you want to assign the soil pressure. So just select the bottom plates first. And also you can do the same as you're working on the other one. So to make modeling faster, I will just select both of the abutments because they will have similar soil pressure. So just go to plate mode, select all of the plate members, mask them, and right now if you rotate the model like this, you will have both of the walls in your view. And here I'm able to select the bottom plates of both abutments. I'm in soil pressure mode, and if you just click these properties here, let's assign it 30 kilopascal. Okay. So if you check for the force, you will see that 30 kilopascal is applied to the bottom plates in my abutment. And always be aware that our local Z will be very important when you're defining the forces. So as you remember, I have assigned a positive value, so the direction of force will follow my local Z, and as you see, my local Z is positive here, so it's using the same direction for my forces here, and also for the other abutment it's the same. So because my local Z is in this direction, if you insert a positive value for the loads here, it will follow your follow the direction of your local Z. So let's continue to assign the triangular force for the other plates. So I'm just going to select them. And T. And the pressure, you can use it, you can do it manually using the soil properties and the elevation of each soil layer or plate here. So for the upper one, I'm going to put 24.5. For the middle one, it will be 19 kilopascal. This one will be 13.5, and finally the top one which will have smaller value, it's 8 kilopascal. So okay, these values are just for demonstration, so they may not be so real, and it's just to show you how to apply loads to finite element plates and abutments. And as you see here, I have applied my loads triangular, starting from bottom to top. This is the manual way to do that, but you can do it always automatically using ADA's generator. So here I have assigned my soil pressure. The other method that I would like to mention here, for example, if you want to model the passive soil pressure you can use spring elements in ADA. So I'm going to show you how to use springs or spring supports to model a passive soil pressure behind the walls. If you want to assign a spring element to the nodes, you need to just go to structure mode and select the nodes. So if I look from this direction, okay, so select the nodes. For example, let's use because these nodes are already attached to our foundation, so let's use the nodes from here in the top. Hold Control, and if you press Control H, replace those nodes as supports. So replace support. Okay, so right now they are all supports, and after that I will release those and put a spring in just one direction, which in this project we will have our springs in Z direction. So let's select our supports here. So to select the supports, go to support mode and selection. Just draw the rectangle here and here. Hit Control H. So I will release all of the restraints here, but I will assign an RZ elastic spring to the nodes. So let's free this RX first. So select the column, right click, replace free. Same for RY. For RZ, we are going to assign elastic support. So change it to elastic for RZ in this project. And we will release also all of the moments. 3, okay. And to assign a value for the springs, you can go to the second tab here, elastic, and assign let's say 10 kilonewton per millimeter for each spring. So right click, replace 10. In this example, for simplicity, I'm using just same stiffness for all of the springs. So I will have same K value for all of my springs here. But as you know, in reality, they will have different Ks depending on the height of your abutment. So you can always modify that by just clicking the spring and changing the value here. So here for this example, for simplicity, I'm just using a constant stiffness for all of the supports. So as you see here, I've assigned spring supports to the abutment wall, and for the seismic analysis, they will be very helpful, and they will model the passive soil pressure. So if you unmask the structure, this is the full structure that we have defined. Don't forget to save your project. The next stage, I'm going to show you how to add some three-dimensional moving loads to our breach here. We have already discussed about moving loads in previous sessions, so here I just use the same procedure. So first of all, we need to define a reference axis for our moving loads. So let's use these edge members here to define our reference axis. So if you remember, we have a selection for those. So go to Control K and edge members. Okay, mask them. So I will use this one. Select all of the members. Go to member mode. Select the members. Press Control H. And here in Advanced tab, you can assign a reference axis for those members. So here, if you move to end of the spreadsheet here, moving load axis, select the column by clicking here, right click, replace here, assign axis 1, okay, and click OK. So all of these members right now, they have been assigned axis 1 reference for my moving loads. So if you unmask the structure, go to view options, pressing O, and put the check mark here in the elements tab, axis 1 moving loads, okay. You will see that the axis 1 is right here, and I will use this to define my three-dimensional moving loads, as you already seen in our previous session on moving loads. So the next stage is to just use ADA's automatic generator. Go to loads, moving load cases, generator. For the code, let's use S6 Ontario. Transitory, normal, and level 1. It will be 3D. The reference axis is axis 1. We've already defined. Let's put in direction 2-way. Delete all existings and have new. And here I'm going to insert the width of my bridge, 1.5 to, let's say, 10.5. And let's use 3 lanes here. Click next. Okay. Okay, I'm going to change the numbers here. So start with 10.5 and 1.5. So the right number should be less than the left one. Next. So as you see here, ADA has automatically defined the moving load cases, and it's covering all of the scenarios possible. So click finish. And as you see here, ADA generated 60 scenarios for this bridge using 3 lanes. If you want to modify the lanes or trucks or the offsets, you can always modify these numbers as you remember. So I'm going to just use these scenarios here, okay? And if you want to view the scenarios, you can go to view options, here, first put the check mark here, axis 1, second check mark, put it here, drop down, and you can check for all of the scenarios here. So if I want to check for this scenario, just click it here, click OK, and here is the scenario. This scenario, it's 3 lanes and it's located like this on my bridge. Or you can check out for other scenarios. Let's say this is the 2-lane one. Okay, this is the another scenario. So we have 60 scenarios on this bridge. So as you see, we have defined also our moving load for this bridge. The next stage is using the load combination generator to generate the load combination, design load combinations. So let's go to, if you remember, loads, load combinations, generator. STX code is okay. We don't have seismic yet. We will add the new ones to the previous ones. We need envelopes, yeah, next. So here put the check mark for moving load envelope. And we don't have press stressing or seismic, so we will leave them as blank. Here in this icon, click moving load envelopes. Make sure you have activated to analyze here, and right click on this cell here, select the code, and select STX, reinitialize, and click OK. So right now ADA will generate the moving load combinations also. Next. So here are the different limit states load combinations, and ADA will use all of our load cases, including the temperature gradient, temperature or other or soil event that we have already defined in this structure. Click finish, and here as you see, ADA is generated all of the load combinations possible according to code. And if you remember, we had our stage load combinations that we have manually defined in previous sessions. So they are still here. Click OK. And right now we can analyze our breach. But before starting the analysis, to save some time here, because I know that the moving load calculation for this kind of breach, it will take so much time, and I don't want to lose so much time in this webinar. So I'm going to remove some of the scenarios, but in your model you can use all of the generated scenarios because you will have time to do the analysis here. To save some time, I'm going to just remove some of the moving load cases here. So I had 60 here. So let's delete 50 of them randomly to just save time on this webinar. Okay. So let's go to moving load cases here. So right now I have just 10, but of course in your model you can keep the all of scenarios, the 60. So click OK. don't forget to save your project and click the design. So click on analysis and design. Yes. Start analysis, and the analysis will begin. It will begin with the moving load analysis. So we need to wait. Okay, the moving load analysis are finished. Right now, AD is calculating the construction stages and other load combinations. Okay, as you see here, calculation is completed. So just click OK or close. So here is the results for our structure. These are the design results for steel structure. And as you see here, we have a little problem here, maybe in negative region for our beams, but the others are fine. If you want to check for the ratio numbers, design load ratio numbers, you will see that it's only here is 4% higher and here is only 10%. So you can always modify your section, and the others are okay. And as you see here, for our piles, most of them are fine, and we have just some small parts here which are a little bit over and they have higher design load ratios here, that you can always modify your sections. And if you want to check for concrete design results, you can always go to concrete mode here and double click the continuous systems. For example, for this column, just double click, click OK. And here, as you see, AD has designed the column, the stirrups, and the main reinforcement here. It has used 1225 Ms for the column. And you can also check for design of a cap beam. Just double click the beam here, and it will be a design of cap beam. Of course, you need to do some modifications on reinforcement. And if you go to view options, here you can check for the strengths and the internal forces, shear and others. So you can always modify the reinforcement, as I have already mentioned in our concrete design, to have better results. And also you can check for the reinforcement design of the abutments. To check for that, you can go to rebar placement mode and use this drop down icon here. So for wall 1, click it here, and if you want to check out for reinforcement design, just click this here. So you will have the reinforcement results for the abutment wall. So this was just an example, so maybe they are not so realistic, but this is how you check the design results for a finite element plate model. And as you see, ADA has used 15 Ms, 20 Ms, 25 Ms, and 30 Ms. And you can see all of those according to their colors here. You can remove each layer or to see just one layer. And also, if you want to check for internal forces diagrams, you can use Control K to mask your beams. And put it as nil here. Control K, beams, mask. And from here, you have access to all of the stages. So let's say for stage 1, this is my moment diagram, and this is for stage 6. So as you see, the integral action, it started to work from stage 6, and in stage 6 I have some moment transfer here, but in stage 1 it's just a hinged constraint. And also you have access to all of your load combinations. So for example, if you want to check for ULS1 max, here is the results for ULS1 max for all of the girders. So this concludes our session today. I hope you have enjoyed it. We have built a three-dimensional bridge with three-dimensional moving loads, and our model includes all of the substructure, superstructure, construction stages, and others. So it's a completely full model for a bridge design. So if you have any questions or comments, just send us an email, as you remember in our help about, and this is our email. And thank you very much for your attention today.